Dear learners, welcome you all in today's Gyan Darshan session. The topic of today's Gyan Darshan session is deletion operation in red-black tree. In the previous session, in fact, we discussed what is red-black and how it can be created and how insertion operation is performed. Now, we will discuss about the deletion operation mainly. So, before we start the deletion, let me quickly go through the red-black tree and its property. In fact, in the red-black tree, we know that it is a self-balancing binary search tree. So, in binary search tree, we all know that for any particular node, all the smaller nodes are present in the left subtree and greater or equal nodes are into the right subtree. And when we do that in order traversal of a binary search tree, then we get data items in sorted order. So, it is red-black tree is also BST, and it mainly maintains a perfect near balance by coloring each of the node either red or black. So, in the red-black tree, as the name suggests, each node is either red or black. Apart from it is a binary search tree. And another property is that in red-black tree, the difference between the deepest path in the tree is no more than the twice as long as the smallest path. Apart from this, we have many other properties. So, let me quickly cover it. As I told that every node is either red or black. This is the first property. Second is that the root node is always black. In the red-black tree, root node is always black. The third property is that no two adjacent node must be red in color. And next property is that every path in the tree, path means from root node to the leaf node. So, every path in the tree must have the same number of black nodes. So, these are the basic four properties of red-black tree. Now, we already know that what is difference between BST and AVL tree and red-black tree. In fact, the AVL BST may be skewed, and to avoid this problem, we have AVL tree in which it is perfectly balanced binary search tree. So, but the problem with AVL is that to make it perfectly balanced, it requires a lot of rotations. So, comes the modified form of it, that is red-black tree, in which we required a lesser number of rotations and it is nearly balanced, not perfectly balanced, we can say. So, here in this slide you can see the example of a red-black tree. So, in this you can see that the root node is black and there are two types of nodes, either red or black, and it is also a BST because we can see that from root node say 5, all the nodes which are toward its left subtree, they are having a smaller value, and all the nodes which are toward the right subtree of the root, those are having bigger values, and this is true for every node. For example, the right child of 5 is 12, so to the left of 12 all are smaller and toward the right of 12 all are bigger values. And also another property is that every path is having same number of black nodes. So, we can see from root to the leaf, in the leftmost we have two black nodes, and in every other path also from say 5 to 12 to 8 to 6. So, there are two black nodes. Similarly, 5 to 12 to 8 to 10, again we have two black nodes. So, every path you see from root to leaf node, you will get that all are having the same number of black nodes, and here in this example it is 2. And the null nodes, in fact the leaf nodes are having null nodes which are always assumed to be black. So, this is an example of red-black tree. Now, I come to the deletion operation. which is a very important operation in red black tree. So in the deletion operation in red black tree, first of all it follows the binary search tree deletion procedure. As we know that in binary search tree deletion procedure, if the node to be deleted is leaf node, then we simply delete it. But if the node to be deleted is having single child, then the node is replaced by its child. And if the node to be deleted is having two children, then the node is replaced by in-order successor. So that procedure is followed in red black tree also. So apart from this, there are several other conditions which are followed. So in fact, in total there are 6 cases which may arrive in red black tree. So let me discuss them one by one and then we will come to the example. So as I told that first we perform deletion based on the binary search tree of properties, whether the node to be deleted is leaf node or it is having single child or having two children. Thereafter, the first case is if the node to be deleted is red, just delete it. If the node is red, then delete it. There is no other changes required to be done. This is the first case. Then second case is that if the root node is a double black, here basically we have double blacks. So double blacks occurs when the node to be deleted is a black colored leaf node and it adds up the null nodes which are always black nodes. So in that case it becomes a double black. So if the root node is a double black, just remove the double black and make it black, make the root black. So this is the second condition. And third condition is that if the double black sibling node is a black node and its child node are also black in color. Remember that double black sibling node is black and its child node are also black. Then we follow the following procedures, sub-steps. First is that we remove the double black and then what we do, we recolor its parent to black if the parent is red. But if the parent is black, then it becomes double black. That is the second step. Recolor its parent to black, right? If the parent is already black, it will become double black. If it is red, then it will become black. Then recolor the parent's sibling with red. So after that, we recolor the parent sibling with red color, or we can say sibling node with red color. And after doing this, if double black node still exists, then we apply other cases. Other cases means whether the case 2 applies, case 3 applies, or the next cases which we are going to discuss further. There are total 6 cases. Whichever the case is applied, we deal that double case accordingly. Then the case 4 is that if the double black's node sibling is red, remember double black node sibling means the parent is same but double black the sibling is red. So what we do in that case, we perform the following steps. What are those steps? Swap the color of the parent node and the sibling node. That is, if the parent node is black and sibling is red, then parent becomes red and sibling becomes black. That is one thing. Then after this, we perform the rotation. Rotate the parent node in the double black's direction. Means if the double black is in the left side, then we do the left rotation. Otherwise, if the double black is right side to the parent, then we do the right operation. That is the next step. And thereafter we reapply. After doing this, there may still exist double black. Then we reapply the other cases which are suitable, whether this case 2, case 3 or case 4, 5 or 6. That is the case number 4. Then case 5 is that if the doubles black sibling is a black node. Doubles black sibling is black node. The sibling's child node that is closest to the double black is red, but for node is black. So here we consider sibling node and siblings children as well. So siblings children, if the near sibling children is red and the farthest sibling's child is black, then what we do in that case? So in that case what we do, we swap the color of double black sibling and the sibling's child in question. Means what we do? We change the color of double black's sibling and the sibling's child in question means the near sibling which is red. So we swap the color of these two nodes. And after doing this, next we perform rotate the sibling node in the opposite direction of double black. If the double black is right child, apply left rotation, and if the double black is a left child, then you apply right rotation. So we perform the rotation as per the situation and thereafter we apply case 6 in this situation. And what is the case 6? Case 6 says that if the double black sibling is a black node, but the sibling's child node that is farther to the double black is red. Here we are talking about the sibling's farther node. If it is red, then what we do? So sibling is black, but sibling's child node that is farther from this double black is red. Then what we do? We swap the color of double black's parent and sibling node. Here the parent and sibling node is changed. Color is changed. If the parent is red, then it becomes black, and sibling is black, then it becomes red. But if the parent is already black and sibling, then it becomes double black. And thereafter we rotate the parent, double black's parent, in double black's direction. That is, if the double black is in the left side, then we apply left rotation, and if the double black is into the right side of the parent, then we apply the right rotation. So these are the 6 cases. So whichever cases are applied, we apply that while deleting a node from a red-black tree. So let me consider an example. And the last step is remove the double black and change the color of the red child node to the black child. Now we consider an example. This is a red-black tree. We can see that it is a red-black tree because it satisfies all the properties of red-black tree. First of all, it is BST, and there are now consecutive 2 red nodes, and every path is having same number of black nodes. And also the smallest path length is not less than the half of the longest path, or we can say the longest path from root till leaf node is not more than the double of the shortest path. So now we want to delete, say, first 10, then 15, then 8. So as I told that, first of all we follow the BST. So we start from the root node and check where the element to be deleted is located, where it is, which node contains that element. For example, the first element is 10, then we go to the root. Root is 5, which is smaller than the element to be deleted. Then we follow the right path, and then we found that it is 10. Then we apply which case is applicable. In this case, case 1 is applicable. Case 1 is that, let me go back and see what is the case 1. Case 1 is that if the node to be deleted is red, just delete it. There is no need to do any changes. So we can see that the node 10 is a red node, so we just delete it. And after deletion, and one more thing, that we can see that 10 is an internal node having 2 children. So which node will replace this 10? As I told, it is in-order successor which will replace this 10. And who is the in-order successor of 10? It is 20. In-order predecessor is 8, but in-order successor is 15, not 28, 15. So 10 will be replaced by 15. And color of the node to be deleted is red, so it will remain as it is. That is, its color will remain red. So after deleting this 10, we will get the red black tree which is shown in the right side of this slide. So we can see that still it satisfies the BST property, binary search tree property, as well as red tree property. So there is no need to do anything further. Now after this, we want to delete 15. Again, the 15 is red node. So which case will be followed? It is the case 1. If the node to be deleted is red, then just delete it using the binary search tree deletion method. So again here in this one, 15 will be replaced by its in-order successor. So what is the in-order successor of 15? It is 18. So 18 will replace to 15. Okay. And here we can see that now the tree after replacing 15 with or deleting 15 with 18, in fact when we replace 15 by 18, then first of all 18 is replaced by its in-order successor, or we can say, because 18 is having only single child, so 28 will first replace 18 and 18 will replace 15. So we will get the red black tree which is shown to the right side. But we can see that this is not a proper red black tree, though it is a binary search tree but not a red black tree. Why? Because every path is not having same number of black nodes. The path from 5 to 4, that is left path, it is having 2 black nodes. The path from root till 18 to 8, it is having 3 black nodes, and the path from 5 to 18 to 28, it is having 2 black nodes. So every path is not having same black nodes. So what is being done in this case? In this case, there will be swapping of the color between the 18 and 28. So we will get, after swapping the color, we will get the red black tree which is shown to the right in this slide. So we can see that now it is a proper red black tree. Similarly, the next element to be deleted is 8. So first of all, we will apply the binary search tree deletion. So in this binary search tree deletion, 8 we search it from starting from the root, we go to the right. Next is 18, we compare with 8, and then we go to the left, and we find that it's a leaf node. Because it is a leaf node and it is a black node, then what we do, we delete 8, but we make it double black, because it is already black and it's a null nodes, whether it is left null node or right null node, it is already black. So after deleting 8, we will get a double black node which is shown in the right side of this. So how we can handle this double black? So in this case, we apply case 3. What is the case 3? Case 3 says that, let me go back to the case 3, and this case 3 says that if the double black sibling node is also a black node and its child node are also black in color, then we follow these steps. We remove the black node, then we recolor its parent to black if it is red, but if it is black, then it becomes double black. Okay, and thereafter we recolor the parent sibling with red, and still if double black node exists, we apply the other cases accordingly. So let me come to that slide. So in this case, we can see that after deleting 8, we get a double black which is shown into the right side of the tree. So what we do, we apply case 3. Okay, we apply case 3 deletion as double black sibling node is black and its child node are also black. So what we do, we remove the double black and recolor the double black's parent and sibling. That is what we do. The double black's parent, which is 18, which is red, and double black sibling is 28. So we swap the color, 18 becomes black and 28 becomes red. So after this, we get the tree which is shown to the right side of this slide. So we can see that it is a proper red black tree. It satisfies all the properties of the red black tree. So there is no need to do any changes in this, and this is the final tree. So this is how we can perform the deletion operation in a red black tree. So dear students, in today's lecture, in fact, we have discussed what is the property of red black tree, what are the cases which arises when we want to delete a node from red black tree. So there are 6 cases which arises, and when we delete any node, then we test which of these cases are satisfied, then we deal them accordingly, such that after deletion of the node, the tree remains a red black tree. That is, it fulfill all the properties of red black tree. So that is all for today's session. Thank you. If you have any question, you may ask.